So my name is Jamie Redding. I'm on the SQL engineering team, responsible for benchmarking, performance, all those kind of areas. So we're going to go through Data Warehouse FastTrack, which is a program we've got internally with our partners to do some reference architectures. We'll spend a little bit of time looking at some of the backgrounds behind data warehousing, some of the technology we use there, and then the actual kit and the process itself. So we'll go through the process. All right. Let's see. Come on. So the first question that we always kind of try and hit is, what's a data warehouse? And if you ask that question, you'll get 85 different answers, and most of them are correct. We've kind of distilled it down to, based on our executives talk about the top parts there. It's where a business goes to get answers to business questions. Kind of distills all the technology behind it. So we're seeing a lot of people trying to get a lot of data coming in now. So you've got tons into the data coming from different points. You've got point of sale systems, you've got pricing information. Just you name the breadth of data is very, very wide. And the problem is, how do you handle that? How do you address it? How do you get information out of it? So people use it for tuning your production. So I know that based on every quarter, in the third quarter of the year, I get a spike in sales. I can plan for that one. I can trend it over time. I can look at my customer buying behavior and figure out what they're buying, how they buy things, and then operationally how I do things. We've done a lot of work with our Xbox manufacturing team on this as well, because they need to know about their suppliers coming in and the output going out and who's buying it. And so they need to be able to make decisions. So they may have these massive data warehouses they put together of all their sales information, their supplier information, and they distill it down to a couple of queries that helps them plan ahead and make sure they have parts on site to do the job.
Very good morning, everybody.
Hello. Wait, was that a better one? So some of the trends we're seeing now, and this is a study we did, actually it's almost a year old now, of data, is that how much data are you managing out there today? And so, right now, well, using 2015 data, almost half or more than half the information is about 3 terabytes or less. Okay, that's big, but not huge. But we looked at what's happening now in 3 years out. What's your plan? What do you think you're going to do there? And the numbers change drastically. So you see the red bar goes, and for 10 TB and more, 34% of the marketplace will have 10 terabytes of data sitting out there to manage. And how do you manage that, and what do you put it on? They're growing at a very, very fast pace. And you've got IoT information coming in, and just the breadth that you can get now from endpoints is much wider now. You've also got problems with scalability. So now you've got databases that used to be a terabyte, now they're going to be 10 terabytes, and then maybe petabytes later on. We've been playing with some large petabyte systems internally. If you've seen the Sky Server demo that we do now for our SQL product, that's a 4 petabyte database now of information from the galaxies, I guess, out there. And also performance is also a big issue. How do you take all this data? You've got 10 terabytes plus of data. How do you analyze it? How do you run queries against it? What do you do with that information? And the other thing is that the storage guys are doing more higher capacity storage devices, so you're basically able to push that data warehouse down to the masses. So it's not in this black hole in the sky somewhere. Now it's down where the analysts can get to it quickly, because the price per terabyte has gone down so much, you can store more data sitting out there. So some of the things that we're doing, and you may have seen these other presentations that we've been doing about it, mostly it's how do you optimize the data warehouse, and this is going to be important later on when we start talking about the actual process data warehouse FastTrack. So for row store information, we normally optimize that for IO scans, IOPS. We'd want to have very fast seeks, because those tend to be point lookups. We also want to keep out a bunch of secondary indexes, because the more you cluster indexes on top of those things, the more it'll hurt the data warehouse performance, but also helps you do point lookups. You're going to have to balance those things out and not do too much secondary indexes on top of that one. If you have lots of rows, so a large number of rows, secondary indexes tend to be a little problematic there and cause us some issues in SQL and internally to get that data back to you as fast as possible. And also adds a lot of overhead as far as keeping the indexes current, keeping the stats up on those things, rebuilding those things optimally. Partitioning is actually the biggest thing you can do today. I can take my database and I can partition it based on a date. Usually the best column to do. A lot of work we do with people is looking at their data and figuring out what we can do with it. Is it a weekly partition? And that makes it much more easier to push in the database, do your bulk inserts in. Also lets you do faster response times, because you can now, rather than querying this much data, I know I'm only working with the first quarter, which is this much data, and I pull that back to you. And the big thing also is data compression. Even though they're pushing storage costs down, if you can reduce your data footprint, that saves costs in the bottom end, and also helps your bandwidth too, because now you can pull in more data at a faster rate across your channel. That's working good. So, looking at a data warehouse, there's a couple of ways you can figure out what the solution should be for you. And we're going to kind of talk about the balancing between flexibility and choice here. So the first piece we'll look at is the time to getting a solution out. So you've said, we need a data warehouse, what should I put it on? So going from the bottom to the top on this part, it's low time to the highest time on the top. So installation on the first part yourself, you get some hardware, you put it in, great, life is good. You configure it, and you start tuning and optimizing it. And that top blue bar could be that size or it could be much longer. It just depends on the experience of your DBAs and what you're looking at. As you move across the line from left to right, the SMP reference architecture in the middle, so that's basically something that's been done by a vendor that says, hey, we think that this configuration, this package, will do it for you. So again, you still got installation, configuration, and tuning, but it's a much shorter amount of time because it's been done for you by somebody else. And finally, we use an appliance. We've got a thing called it's called APS, and it used to be called FTDW. So basically an appliance system, which is a prepackaged, here, buy this rack, drop it in, plug it in, you're ready to go. Much easier installation, configuration. It's all been tuned and optimized for you. Just throw your data on there and go. So that's the first piece of it. The second piece is how much does it cost? And that's always a big concern. So the bottom chart for price is top of the chart's low, bottom's high. So getting the hardware could be, if you already got it, that's pretty easy, that's pretty cheap. If you've got to go out and get it in, that's more cost. And then you've got to do your software. So doing it yourself or doing it with the reference architecture is pretty much the same because you've got to get hardware, you've got to get the software, and you're ready to go. With an appliance, it's a little bit different because now you basically go buy this thing and you're pretty much done. It all comes in the box together. So from the offering standpoint, if you want to do it yourself, you can buy Windows Server, you can buy SQL Server, and you do your tuning, your installation, your configuration, you're done. Pretty simple. The middle column, what we'll talk about more about later on, is Data Warehouse FastTrack, which we'll talk about go into more detail later. Basically, it's a way to fill that box in and say, this is what I need to buy. I buy the package, not a appliance, but a package of hardware that then I can then run my data warehouse on. And finally, the last one is APS, which is our offering for appliances. So, what is Data Warehouse FastTrack? Well, it was built actually in the old FTDW days. About 4 years ago, we started doing this. And it's a way to give a customer, the end user customer, a proven platform. So in this case it was an appliance, but we broadened it now to other systems. But they know that this configuration of CPU, memory, disk, all the connectors between those things, all work for data warehouse. It's not done by us. We build the kit and the software for it, but the actual people that run the benchmarks are the hardware vendors or storage vendors that make that product for you. So they actually do the actual work for us. But we help them with it's a joint effort between the two of us. It also helps the customers deploy these things because they know it's a proven configuration, so it reduces risk, the cost and complexity of it. It also gives them a kind of a better warm, fuzzy feeling that this thing will actually work for them versus going down a path saying, oops, this didn't quite work, I need to change my storage out or whatever else. And so finally, the end point of the whole thing is to build a database reference architecture that lets a customer use that as a point going forward. We've seen or heard anecdotal evidence from a lot of our partners that these are actually used in sell situations. They'll go in and drop the reference architecture on their desk, says, your data warehouse is 10 terabytes, this thing will fit it with some growth, and the guy buys it and you're done. So it's been a pretty successful program from that standpoint. And that button didn't work. There we go. So what we try to do in this versus other workload, other benchmarks, like a TPC benchmark, for example, is we try and take a holistic approach to it. We know that you can get a really fast processors and really slow storage, not so good, or vice versa. So we try to get a nice holistic approach where each component is optimized for its place in the chain. We also look at the whole thing as a full configuration versus we don't just do CPU tests while we can do lots of instructions per second. Disk is bad, so we try to make sure that we're doing the whole thing across the entire platform. So the benchmark kit is designed to run and read the real bandwidth across each component. So it's not just an isolated test. We also try and go through and make sure that each component gives enough bandwidth for the workload. So the workload in this case is data warehousing, so we're not looking at OLTP performance. It's just data warehousing. So a couple of examples that we normally see when we start working with a partner or something is we'll see a case where the CPU is sized properly. The I/O channels are really high bandwidth there, but the I/O capacity for sequential I/O is pretty tight. In that case, you don't quite get the full benefit of your throughput of your system. So you're basically, I got really good storage, I got really good CPU, but I'm missing something else in the plan. So the storage system here in this case is constrained. We also see places where it's different. So now you've got CPU's fine, the I/O channels now have the problem, but storage is great. So again, you don't have that true balance. You're getting good performance, but you're also wasting a lot of performance on the floor because you're not using all your CPU, or in this case, all your capacity of your system. Again, we can go through more things, but basically it's something is always constraining the box. So what we're trying to do in the Data Warehouse FastTrack program is to get to a state where, it's not talking to me. Okay, let's try again. Here we go. Get to a state where we have a balanced system where we're using as much CPU as possible and keeping those things high performing. We build the system to take advantage of the full throughput of the I/O subsystem, I/O channel, and there we go, a little slow. And we're also using the capacity storage box so we get the full maximum throughput of the system. Here we go, God, it's a little slow. So if we balance those things with the tasks we do today, we can basically maximize what we get out of the box at that point. So the methodology. So we take this whole thing and we try to help you keep from overspending on CPU storage or whatever the different components are. So basically, those are what we see at the application level. So I buy really fast processors, really slow storage, but the end user doing the consuming of the application on the application side doesn't see those benefits. They lose something in that process. We also hope this thing gives you kind of an out-of-the-box performance that you can predictable. It's predictable. So if you're certified for a certain size, then you know you'll get that out of the system. Now, if you go bigger than that, there may be a range where you actually crossed over some boundary. Now we're out of balance again on either CPU or disk or something. So it kind of helps you give a out-of-the-box predictability for that one. We also want to do a workload-centric. So we could do I/O meter, we could do disk speed tests, we could do all kinds of tests on the system and say, well, this is a really great I/O subsystem, but rather than doing that, we took a workload approach. We have a bunch of DW queries that run this thing, so we basically get a holistic look across the whole system, and we don't lose any piece of it in the distillation of the test data coming back. Now, what we do in Data Warehouse is one of the features, or we probably may have seen other presentations as well for SQL Server, but we do use page compression in some cases. So that was brought out in SQL 2008, which has been a while now. So it's mostly for our row-based systems, not for column store. We get 2x to 5x data compression depending on the data. I've seen some cases where it's a little bit higher than 5x, but mostly that's the good range to think about. And usually it's for smaller tables, so less than 1 million rows or so. Anything more than that, it starts to have issues with trying to decompress the data back out to for the processor to use. The biggest thing we did actually was in 2008 R2, and then we did subsequent iterations of it, was the columns or index. And we'll talk about that in a little more detail later on. So it puts the data in a column format versus a traditional row format, and we get at least 10x data compression. That's just inherent in the system. And for queries that touch those rows, it speeds them up significantly. I mean, some cases we've seen 15, 20x performance improvements on the queries across the line. For larger tables, it's perfect. For smaller tables, the benefit drops, but for those big, massive fact tables, 60 billion, 70 billion rows, makes a huge difference in query performance. Other big thing we did was we started doing called operator pushdown. So there are things you do in data warehousing queries where you want to filter data or aggregation queries. Well, those are normally done in traditional row stores at the query processor level, so it moves up a little bit. We've pushed those down in the stack so it's closer to the data, so we actually do that processing much closer and not give the QP back as many rows. So I'm filtering a 6 billion row table down to the 30 rows I want. Rather than giving him back 6 billion rows, he gets his 30 back and does a final processing and sends it out for you. That makes things much faster and much more efficient on the back end. And then finally, we do batch mode processing. So in traditional row store, we did things a lot of times we do a row at a time and process through this thing. So now we can do that a little differently. We can use a thing called SIMD, which is from Intel's processors. We can do a bunch of things in parallel across multiple rows of a database. So it basically allows us to batch up several things at one time, coalesce them back at the qubit level, and get the data back to you. So it's much more efficient using the processors at their full capacity. So column store. So the traditional way of doing it is row store based. That's the picture on the left there. Data stored in rows. It's pretty simplistic. We know that one. Great for OLTP data and really good for small sets of rows. Really good for inserts, updates, deletes. You just add new rows, you take the old ones out. Very clean, very quick for those systems. So, but not so good for data warehouses. So we brought out, there we go, the column store index. So now we take the data and kind of flip it on its side. And now we look at it, think of it as columns of information versus rows of information. So we basically sort it on or coalesce it by, for example, a date field or a customer ID field. And it's stored in things called row groups. So that's the row group goes this way, so it looks like the different row base. And then a segment, which is the actual column itself. Why is my thing not working here? I'm getting too far away. And that's the segment. So it helps us do different things. For example, on some of the queries with the operator pushdown, we can do segment elimination. So we know that when you ask me, give me a query that asks, we'll touch 6 billion rows. Based on some information the QP gets on that one, he can figure out, well, I don't need these 40 segments, just these last 20 segments, because my data is going to be in there. So he eliminates that from his complete search pattern. So again, it makes it much more efficient. We also get better compression because now we know information in the same domain. So same type of data, date data, for example, if you're doing a weak partition, I can compress that down because it's the exact same date inside there every single time. So it gives me better compression because I can look at the data a little more better. I get better I/O. So now rather than having to go back and grab an entire chunk of data, I get the columns I want, nothing else. So again, it makes it more efficient. So in the case of a query that would be, if you've got a table that's pretty wide, you bring the whole row back to look at it, to process it. Now I can just pull back the columns I want from that same wide table. Again, more efficient on the back end. Improved performance. The column store itself lives in memory. It's backed up by disk tables, but it lives in memory. So if you've got enough storage, then the query processing is very, very quick. It also allows you to do better CPU utilization because now it's all in memory. I can process faster. I'm not waiting on disk I/O to bring stuff back in for me. And again, it's ideal for big tables and data warehousing. Golly. I have to fight this thing in a minute. There we go. So there's a lot more indexed or detailed presentations on the column store. It's really good technology and very easy to use, and actually in most cases transparent to the end user. The DBA has set it up just right, but once it's done, the queries come in and no one knows the difference, so then they came back a lot faster. So some of the benefits, we talked about better compression, better query performance. We store the data not in row groups anymore, but or not in rows, but in row groups. We normally batch things up about 1 million rows. So one thing I'll talk about in a minute. So the BAS part, the update and delete operations. So yes, column store can do update and delete, but it's not optimal for that. So if you do, for example, if I do a delete or an update, I actually have to take the row, change it, put it up in a delta store, which is the changes that happen in my data, and then mark this row as not in use anymore, or this column not in use anymore. So that's not as efficient as an OLTP system doing to the row base. Row base, you just keep on going and we reindex as we go. So it's a little more difficult, and what will happen is those rows in the delta store, you get about 1 million changes sitting out there. Then it takes that, compresses it into the column store, and pushes it back in. So a couple painful things happen there. One is queries that have to go to the delta store a lot take a little bit longer. And that compression is not free. So I take those 1 million rows and I compress them down into the column store. That takes some overhead, some CPU overhead. So that's why column stores are better for things like data warehouses and not OLTP systems. So that's one of the big paces there. But what you can do though with column stores is the space used is pretty significant. So this is a 101 million row table. So a table with normal indexes. So a row-based table, standard indexes will take roughly, say 19 gigabytes of space, give or take. If I take those and I throw some indexes on top of that, when I do page compression, I can push it down almost half. So a good thing. The table itself, raw data, no indexes on top of it, roughly 5 gigabytes. If I take that, now I have no indexes and I page compress it, now I only get just a little more, probably about 4 gigabytes or so for that same table space. Now we're getting better, but not great. So if I add now a non-clustered column store, which is the duplicate data, so it's non-clustered, we go back up in size now. But now I'm getting a column store index, so I get some benefits from the query processor and the speed of that one. And I'm also getting, at least from the case of the table with normal indexes, I'm getting, a third of the space used for this one. But if I can drop on top of that a clustered column store, which doesn't duplicate the data, it's the same data on both places, it drops down very small. Now, up to 90%, that's a marketing number. So that's why it says your mileage may vary in the bottom. All depends on the data. We've seen 90% in some cases, we've seen 30%, but you at least get 10x the compression. It's a pretty impressive technology. And again, the minimal overhead from the DBA side is minimal, and the performance in the queries from the user side is amazing. So, you're a sponsor, we have one in the front row here, and you want to do a data warehouse fast track. What do you do? So you contact us, and we give you a spreadsheet that you need to fill out. It's a reference document, and we'll look at an example in a few minutes. And that document basically tells us what you want to do. It gives us information about your system, processors, cores, memory, disk, the whole bit. It's a pretty detailed information we need back, and so that's the first cut. So they give it back to us. We do a quick analysis of it, make sure that you're not, at least from the surface, not out of balance. You weren't wasting your time. So we come back and say, okay, great, looks good, let's go run the test. So they'll start running the tests on the row store and the column store. We do both configurations because it may be different. And they run different configurations of different streams, different parallel sessions at a time. They do CPU stress, they do IO stress. So basically, it's at least 8 hours of runtime. So what's one test. And if all went well, they pass it all back up to us somewhere. There we go. Oops, too far. They pass it back up to us along with a ton of other data. We ask for SQL error logs, we ask for perfmon data, all kinds of tuning information to get back. We take that information, we analyze it, and make sure that everything looks good from a balance standpoint. And their whole goal is to have a balanced, holistic approach to this thing. They get the spreadsheet, we look at it again, and then we come back and I have to have a leash, I think, on this thing. So give it back to us, we review it, and we give the final certification. So that never, ever happens in the real world. It's not that quick and clean. You're not done 8 hours, uploads, certificate, go home for the weekend, it's great. That process can go on and on and on and on and on and on and on. And mostly it's a case of us trying to help them get the best performance out of the box. So that may be changing resource governor settings to be a little bit better, or doing more degree of parallelism, XDOP settings for their system. Also just basic IO tuning in some cases where they've got a misbalance in the IO system so we don't get the performance out of it. But once that process finally finishes, we give a certificate back to them. We'll see an example in a few minutes. And they'll have to write a white paper or a tech brief. And this all gets posted to Microsoft.com in a data warehouse FastTrack system where references are. So they can use that. We kind of do some press for them as well. They do their own press, and that's in use for the marketing people to go out and talk to customers and say, hey, you've got a data warehouse need. Here's a size that you're looking at. Here's one that we know will work for. It's been certified as having the capacity and the performance to give you good performance there. So to get those things, we've done a couple things that may seem artificial, but there's actually method behind the madness here. So first of all, we use the data warehouse or the TPCH schema and data and queries. There's different opinions on that thing. I'm part of the TPC, so I was actually responsible for some of the TPCH stuff, unfortunately. There are some warts on it, but it is a known data set. It's very repeatable, so it gives us a nice place to kind of start off with. See, every test you run is an hour long at a minimum. Some cases will run that same test 4 or 5 times. You get the right numbers out of it, but that's basically every test is an hour. We also measure both IO stress. So we basically change the configuration so we push the IO system really hard and also push the CPU subsystem really hard to make sure we get that good balanced approach. Do the IO tests, we actually don't allow you to play games with memory, because you could pack the box full of memory and get a great score on the IO test because it's all cached. So we actually force you to lower the memory that SQL can see on the box based on the size of your system. So again, for 1 to 2 system, we basically have you set max server memory to 118 gigabytes. You could have 4 terabytes in the box, don't care, SQL only sees 118 gigabytes. And it moves up on those same platforms. And that's to force the information to go onto the disk and not just come from the cache. But the corollary of that thing is you can't just then put a configuration that has a small capacity of storage memory in the box. So based on what your box looks like, number of sockets, and if what you were certified for, which we'll look at that number in a minute, the rated capacity, you have to have some minimum amounts of configuration or memory you can support in the configuration. Now, does that have to be in there when you ran the box? No, but you must be able to support it. So for example, it's a 2-socket box with a 60 terabyte database or certification. You have to have 720 gigabytes of available storage that you can plug in the box. And if your box only supported 256, we wouldn't certify it for you. So there are some minimum bars to get over. Has everybody seen the TPCH schema? Because it's kind of weird. It's supposed to be, well, it's actually, what, almost 20 years old now. You can almost drink in most states. It has some issues. We'll talk about those in a few seconds, but basically it's a well-known schema. Most of the work we do is on the order line table, because that's the biggest one in the system. So most of our queries touch order line, but it is a semi-normalized star schema. There's some negotiation or some controversy on that one as well. Again, it's just an old database, but again, it's well known and well repeatable. I went too far. There we go. So, but why we use is because it's getting predictable. So we know what the cardinals look like. So we basically support 3 database sizes: 1 terabyte, 2 terabyte, and 4 terabyte. Now these are not, well, 1 terabyte is a official TPC scale factor. The 2 and 4 are not, but they scale the same way. Those are kind of the row counts, the cardinalities per the tables. Why we touch on line items so much is because that's the one that kind of mirrors a real data warehouse. In the smallest case, looking at roughly 6 billion rows, and then 12 to 24 billion rows, you go up to scale factor there. So those are the 2 we mostly hit. We don't really touch most of the tables because they're there for supporting, but they're not really there for the true performance metric. So we do have 3 queries, and we'll look at those in a few seconds, what they look like, and we run them in a 1-2-3 ratio. So we run 1 complex, 2 average, and then 3 of the simple ones. And those run in a kind of a random fashion, but they run for an hour. Previous versions of the FastTrack kit let you run until all the queries were done. It was kind of a long test and didn't really prove anything, so we went back in and re-architected it a little bit. We basically run for an hour. Now that last query may not get through, may be done. Doesn't matter, we kind of toss the front and the back off and just use the middle set of them, which gives us, again, a good predictability performance. So based on your system size, number of physical sockets, that's why we picked the database size, so 1, 2, or 4. And that's cardinal we saw on that previous screen. And we do have a couple of bars to get over. One is for all your runs, you must have at least 60% of the CPU consumed. And the reason behind that is that we don't want you to, well, we want to keep our balanced system. So if you're using 10% and still getting decent performance, you've got to balance at that point. You're not using all the capacity of the system. And plus it also, if you don't run quite 60%, we find it tends to hide some flaws somewhere else in the design, mostly in the I/O subsystem. So we're not getting query performance, but we're seeing something else chewing up the CPU for us, and that's usually I/O weights, that kind of stuff. So again, it just proves an imbalance at that point. So we also put a thing in, so we had some issues late in 2014 where the column store was so much faster than the row store because of the way their system designed that it kind of left us feeling uneasy about certifying the system for that rate. So we actually put a cap in this year for the 2016 version of it that it must be 1.6 or lower the ratio of those 2. Again, that's to kind of keep that whole balanced system. So you're not building a box just for column store because it might be used for row store as well. Again, trying to keep the balance in the system. When a sponsor does a test, they have to give us all the error logs for all the runs to make sure that, one, we can verify the settings for SQL were set properly because it's all dumped in the error log for us. And also that nothing happened during the run. IOs are waiting too long or something else that may have been missed by the sponsor. We want to know what their settings were for SP configure, the settings for SQL Server, and also anything to do for the resource governor. So we recommend highly for data warehouse workloads that you enable the resource governor. It allows you to configure CPUs, schedulers, memory, how much of a particular process can go in and grab memory. We set most of those to be about 25% for data warehousing queries. That makes sure we get enough memory for the query to actually do his work, plus not start pushing out some of the column store data back out of the memory. So we'll make sure those are set properly for the workload. So the queries themselves, this is a simple query, and it's actually pretty simple. We're touching line item, which in the case of a 1 terabyte 2-socket system is about 6 billion rows. We go out and we grab some sums, we come back on these criteria. So this is the part where you see the push down start to occur for predicates. So in the where clause, we're looking for L discount between those values. Before, we would go ahead and grab all those rows that kind of fit this criteria and throw them back in the QP, and he would go through and process those predicates and push them out for us back to the end user. With the predicate pushdown, those, and as well the equality for L quantity, are all pushed down close to the data when we execute it. So we only actually grab the rows that fit those criteria and then push them back to the QP for the final processing. So it makes it much more efficient. So we run 3 of those, we run 1 of these, or actually 2 of these. This is the average query. Again, so we're still touching the line item table, which is the big, in the case of the 1 terabyte, 6 billion rows. We're doing a little more information here. We're getting more sums. But the biggest thing that hits us here is the where clause with the date. So we're doing a date offset for the ship date. This is also going to predicate push, it'll be pushed down close to the data. Then we'll do the group by and the order by. So the order by is still done by the QP, but the group by is now pushed also down to the predicate processor. So we get the where clause, the filtering out for the date, and then also the grouping happens down there because we have data already sitting there in our buffer. We push it back to the QP, it does the final order buys and the final sums, and then pushes it back to the end user. Again, much more efficient. And then the complex query, again, touching line item. Actually, we're getting 2 tables this way. We're touching line item and part. So part is not quite as large, but it has some foreign key references back to line item. And we're basically doing a case statement. So we'll do 1 of these, 2 average and 3 simple in a known random order that we can predict, for the information coming back for us. Again, same thing here. We get predicate pushed down on the where clause. In this case, through part, ship date on both those columns there. So one thing we'll look at in a few seconds is everything is based off of relative performance. And so that's based on the original certificate 000 we published, which was a reference configuration we did internally. It's a 2-socket Intel box. There's the stats for it up there. We ran it. It gave us a capacity of 25 terabytes, and we set these relative throughputs for roaster and comp at 100. So it was an arbitrary number we picked. It was easier to use that versus 0. 0 sounded bad, so 100 sounded better. So basically, everything is based on, from that point on, is based on this reference configuration. This is not one we publish. It's just out there for our partners to use. So, got too far away again. There we go. So those metrics we're looking at. So there's basically four metrics you look at. So one is the roaster relative throughput. So this is how much faster is your configuration than that Intel 2-socket we used a while back. That's all it means is if it's 125, I'm 20% faster than the one that's 100. If it's 75, I'm slower than that configuration. The columns are the exact same process, but now it's based on the column store information versus the roaster information. And we'll look at an example of one of these in a few seconds of what that actually means on the certificate itself. We also go back, and these are the ones that most people focus on versus the relative throughput performances. First of all, what will this thing handle? The rated user data capacity in terabytes. So we calculate this value based on the roaster information, the column store information, the storage, physical memory, and basically we do a bunch of run it through the black box, and we pop in a number that says this thing will do 25 terabytes. So based on the performance of the system, the IO subsystem, the channels involved, that this thing will give you, will handle a 25 terabyte database very well and give you good performance. We also know that that's not real stop. You'll be, we saw that chart earlier, things are growing, so 25 terabytes today may be 50 terabytes tomorrow. We don't know that, but so we give you basically what the maximum capacity will be. So if you were to use all the storage in the system, we don't use it all for the test, then you can go up to X terabytes based on that one. The one thing that we do make an assumption that may or may not be true in all instances, we assume 5-to-1 compression ratios. Mostly that's middle of the road for us. We can get better in most cases, but that kind of gives us a place that, well, yeah, if your data is not compressible as much, then you may not get these same values. It's kind of our get out of jail free card there on that one in case there's an issue with the sizing of something. Those are the two main metrics you look at, the rated user capacity and the maximum capacity. So this, a little hard to see, but is the reference configuration certificate for our reference architecture box. So it gives some information. It tells you what the system was, the processor types, how much memory is on the box, so that what was configured with, not what we use. Remember, we cap it for SQL Server. Operating system, database version, and then the storage information. This is actually really interesting information. So basically it tells us what we did for data in TempDB, how it's configured, how it's laid out. what we did for OS to put the operating system on, and then for our SSDs for logs. But the metrics now pop in those boxes below, and there's a lot of information in this chart. So the first one is the one that's kind of grayed there, is the one everybody looks at. That's the rated capacity. So this configuration, if you bought it, put it in your data center, load it up, you could handle 25 terabytes of data without any problem. So this is the one that's a reference. It's 100 for both the throughput, the ratios for relative throughput, and then it'll handle up to 28 terabytes. Because the disk that's configured, it'll take 28 terabytes before it runs out of space or has issues with it. We also went ahead and dumped out the different performance characteristics for both implementations because we know that everyone wants to go column store. We recommend it highly, but it may not make sense in all cases. So we did the row store test, and we basically gave back some information about how many queries per hour per terabyte did we do during the runs, what's our scan rate on the drives, so how many we did that when it's all measured, the logical scan rate, the measured I/O throughput, and then finally what the CPUs are running at the time of the test. So kind of a sanity check, some for our point as well, but also to let the end user, the customer, know that this configuration get this performance back out of it. Now, these are not the maxes, but they were real-time, during queries, measured performance. And same for the column store. And the very bottom is a bunch of disclaimers about, well, this is based on a reference configuration, and your mileage may vary, and this is based on, kind of explains some of the information below. Oh, too far away again. Here we go. So this is also the information we actually pull back from the end user, if the sponsor doing the test for us. This is part of the spreadsheet. So all the perfmon data is all collected and uploaded back to us, and we'll distill it down to these columns in an Excel spreadsheet. And the information here is interesting as well because it talks about, see the run one, we know that this is a 1 terabyte database. We know it was 118 gigabytes for SQL Server memory. We know the DOP was 16, RG was 12% for this run. And then now we have the raw data to back this up that says, well, this system doing 12 streams, the top line there, did 3,409 megabytes per second read on the physical side, and then 3911 on the logical side. So this helps us kind of make sure that we're on the right track as far as what this thing is doing. And we can look at here, and you can actually, this is where we do a lot of that, the iterative process of you run it, and then we come back and you run it again. Based on this, that's how that happens. We come back and look and say, well, yeah, while your CPU was low, we need to make some changes and run it again, or something's out of balance in your reads per second. They don't look quite right for your disk substance. We know what that change should do based on the specs of it. You didn't get that much, so it's an iterative process. We're trying to figure out what happened in this system and what we can do to make sure it performs optimally. So they have both the row store on the top and the columns on the bottom. And this is the part where this system may last weeks. In some cases, we've had a couple months going on with sponsors trying to get this thing tuned just right. So this is one that was actually, I think, announced Monday maybe. It's a brand new one from Lenovo and SanDisk. So you notice it's a different storage partner. So in some cases, it's the hardware vendor, in this case Lenovo, would publish it and do all the work. Other cases, the disk vendor may do it and partner with the hardware vendor to do that piece of it. So, like I said before, it's the same information we saw on the reference architecture, but a little better now. So now we've got system name, what the processors look like, how much memory is in the box. It's a 3 terabyte system. This is a 4-socket, so it ran a 2 terabyte database. We capped the memory on it as well. Windows Server 2016, SQL 2016, and then the SanDisk information there as far as the disk they use. And then the capacity in this one, so our reference architecture was 25 the terabytes. This is a 145 terabytes. So we feel confident that if you were to buy this thing and throw 145 terabytes at it for a data warehouse, it'd work perfectly. And the max on this one is 187 based on the available space for the storage. And you can see the numbers there. So our poor little 2-socket Intel box from 2 years ago was 100. This is 459 now on the row store and 734 on so it's basically 7x faster than the old one. Now, price is probably different as well, but it's a much faster system. And the details below that are from the row store and column store. Here's my commercial for Lenovo, so they asked me to do this for them. They're in booth 1010. They're actually showing this system. They've got it running over there, and you can look at it and touch it and that kind of stuff. So, but a very good result, and I think our biggest one so far. So the question that always comes back when we talk about these things is, well, okay, great, I got this thing, it's got 50. Well, what do I do with that? What does that mean? So kind of with a little exercise to kind of show how a customer can use this, or a sponsor or a vendor can go back to a customer and show them how to use this information. So first, assumptions. So X and Y configurations, they're pretty much similar in price, but Z is the Cadillac of the line, so it's much more expensive. That's pretty simple. So then you gotta do some questioning on your data is, if you can get lower, if your compression is not as good as 5 to 1, then probably X is better than Y, because you get a better future growth with X. So you know you can't quite do 5 to 1, so I can actually grow into 80 terabytes for X, where Y is only 55 terabytes. So there's extra headroom out there for me to play with. Also, if you're doing column store, then X is a better approach because it has a better column store number versus the Y. So again, it's multidimensional to figure out what the right answer is here. If you're a row store-based solution, though, you don't really want to do column store, row store makes more sense for you, then you go with Y because it has a better row store performance. Now, if you had the cache and you want to do it, then Z is probably the best across the board. It doesn't have as much headroom as the X solution, but it does have great performance on both the row store and column store. So it's one of those things where we can't make the decision for you, but it kind of walks through the process of how you would take competing information from different manufacturers saying, mine's better than his. Well, maybe not in all cases, because the numbers and the rated capacity are exactly the same, but there's different analysis and different nuances you can pick out from the information that's inside there. So we've always worked with hardware partners. I've been at Microsoft 18 years now, and my job from day one was to work with these people. And they've, some have come and gone, some have changed names, but we pretty much stuck with the guys that make the system units, the processors, that information. That's been our TPC realm in the past. All our benchmarking is done with those people. But the Data Warehouse FastTrack program has changed a little bit. And I mentioned before there was that SanDisk report from Lenovo. We now can do a lot more things with more players now. Didn't have them in the past, so we kind of knew that they were out there, and we kind of talked to them and stuff, but we never really worked closely with them. And this program has changed that around quite a bit now, so we get a lot more excitement and enthusiasm from the disk manufacturers because they can show off their storage and partner with the hardware manufacturer to do their server side. So it makes a little broader area to play in now for us. So right now, there are 42 published results for SQL 2014. Back in late March, early April, we rolled the program to 2016 only, and there are 10 now either published or in flight. There's a couple that didn't quite make it this week, and they're still working on it. And I think if I can get to it, this may be an adventure. If it'll show it. Maybe I can't show it. Anyway, we'll just fake it. So there is a website, if you do a search for SQL Server Data Warehouse FastTrack, you'll pop to a website that has a list of all the publications out there, and they link to all the white papers or tech papers that are published. There is requirement in the program once you do this that you do publish one of those papers for us, and it explains the configuration, it explains how they put it together, all the metrics they got out of it, and then a bunch of information about how you should interpret those metrics. And that's the piece that we really ask for. The certificate is nice to have, but the actual white paper is what makes the most impact with an end user customer. So we had discussed doing a demo, and I started watching it, and it's like, well, this is really boring. It's you push a button, you come back in an hour. It's like, well, that was not really exciting. So I wanted to walk you through just a little bit of some of the screens that kind of show you how we made it easier for the end users to do this kit. So these are a couple of screenshots of the actual kit itself. We ask a bunch of information. We ask, tell me what your substance looks like. Fill in the blanks. So we want to make it as easy as possible because if we can make it easy, they'll do more benefit to the end user and the customer at the back point. So we ask them about where things live, what their system looks like, how their data is laid out. It's almost traditional Windows GUI-based stuff. We want to know what your storage looks like. How are you? Anything you can tell about the system ahead of time will help us do a better job of running it in the future. How you configure your disk subsystem. We also want to know, database names, how big this thing is, where we're going to get the data from. So again, tell me what you want me to do, and I'll do it. So this is all the setup process. This is before I've even done a single run. I'm just trying to build the database and get it set up. Oops. Let's go to the fun stuff. So now that I'm ready to start doing a run, I can do some either single testing or I can do multi-stream testing. You give it a name, where I'm pointing it to, and I can pick some queries. In this case, I'm doing a 12-session I/O subsystem test. So it'll behave differently than a CPU test it'll try and drive more I/O to make sure we can actually stress that I/O system enough to get a meaningful number out of it. So when you're all done, you would go down to the bottom and click the Start Test button, cross your fingers, come back in an hour, and you're done. Click the data, it's all put together and package it up for us. But you do that 8 times at least, if not more. You can also pick multiple things. So here's all the different configurations we support today as far as CPU I/O stress. So if you are wanting to do just a 1 session or want to do 48 sessions, some of the bigger systems, the 8-socket boxes are now doing 48 sessions because it can drive more CPU for them and push their system to the end. But basically it's as simple as the sponsor clicking on what they want to do, clicking on Start the Test, and they come back in an hour. So we're trying to make it, again, as simple as possible for them to get their information. If you want to, or actually here's a list of what we actually run. So these are the queries we can run. You can either run them as part of the simple, average, complex environment where you don't really know what they are, we saw them, or you can go back and actually run the real TPCH queries against it. This is useful mostly for debugging purposes when we get a problem where, wow, this thing doesn't look quite right, there's something odd about it. We know these queries very well. We can have you go back and run query 6 because we know it should behave this way. If it doesn't, then it points back to an RG problem, a memory problem, or something else. So it kind of helps us, again, to make sure that we're comfortable giving that certificate out to the end user and not misleading something in the back end. And important. So again, anything you want to do, you can build packages for it. It's also done by the user himself. So in the future, we're trying to actually in the planning stages now for bringing out a new FastTrack kit for next year. We've been asked to do things in virtual machines. We go back and then internally, it's more of a religious war on that one. Is some people think, data warehouse VM, no, never happened. Like, well, no, it can happen. VMs have gotten to the point now that they have the capacity, they have the storage bandwidth that we can do that. So our next jump will be into doing VMs as well as bare metal. The cloud also wants to play as well. So we're working with Azure now to do things with SQL Data Warehouse, SQL DB. And we're also working with people like Google and Amazon because they actually host SQL as well. So they'll be working with them in the next year to do results on Amazon and Google in their cloud environments. One that's near and dear to my heart, SQL on Linux. That's the project I'm working on now. Basically, we could do it today because the kit will run on Windows talking to a Linux box in the background. That's not as attractive to most people doing Linux, so we want to make sure you port the kit over to a Linux environment and then run that thing natively on that one. The last two we're not sure we're going to do those yet. We've had requests to try and layer some R analysis on top of the database. We're not sure really what to do with that one yet, but we've had the request several times from both internal people as our partners, even a few customers who use this for their benefit, and as well as Polybase. So those are the 2 areas, but the other one is, you may have heard of HTAP or Operational Analytics, or it's got 18 different names. But basically, it's taking a OLTP database, which is different for the data warehouse FastTrack, but layering on top of it a data warehouse query subsystem. With the column store today, you can do that now, and I think demoed it on the keynote the other day, where we have a traditional OLTP database churning 1,000 transactions per second, and actually injecting data warehouse queries on top of that into the column store. So the OLTP system continues to run like it normally did with B trees. So insert updates, deletes are very fast. But later on top of that is a column store that looks at that same data. And then we can then do analytics queries to those things. So that's the one thing that we're looking at strongly because that's at least internally from Microsoft's standpoint, that's the big push for the future is HTAP. They also came out of due to the Xbox manufacturing people, they have to deal with thousands of suppliers bringing in thousands of parts to these manufacturing lines. And if a bad part gets through, they want to know as quick as possible that those parts are bad, pull those boxes off the line, refactor them, and go back in. Without having an HTAP or an analytics query on top of their OLTP database, they can waste time, money to get those things resolved. So that's the new push for it. I think with that, I'm done. Any questions? I can't see. Yes, sir.
On the resource governance, any rule of thumb starting point offer what you start out?
So for data warehouse, we always start at 25% for the memory grant. That's the hard, fast rule to start off with. And then based on, so If you run that in isolation, so I have one query and I run it, it'll work great. But now I start running 10 different queries all at the same time, you may see that number, the queries actually go down a little bit. So you start walking the RG down a little bit. So usually we sit on our small 2-socket system, we probably put about 12% because that makes sense in that configuration. But a larger configuration with more memory, then 25% is a good place to start. Anything else? Sorry, I can't say. All right, then thank you very much. Anything else come up? Be happy to answer questions up here if you need to. So thanks. All right.